Start.
Excellent. Can you hear me now? Hello? Excellent. So you can hear me now.
Yes.
Perfect. Okay. Let me put a timer. Great. Okay, so thank you so much to the organizers for putting together such a nice conference and for inviting me to share my work. So today in these 20 minutes that I have, I'm going to tell you a little bit about flat space quantum gravity. And instead of working with real-world models, I'm going to consider a toy model and show you everything we can do with a toy model and all the things that we can learn using this toy model. And hopefully, the hope is that using such a toy model, we will be able to learn some kind of lesson that will help us to approach the problem of understanding flat space quantum gravity in a more realistic case. Okay? So let me begin. I don't think I'm saying anything new when I say that quantizing gravity has been extremely subtle and challenging. And as I just said, the idea, the approach that I'm going to be taking is that I'm going to consider a toy model, and by that I will more precisely refer to a two-dimensional theory of gravity instead of a four-dimensional like in our real world. And the hope is that some of the lessons we learn in this simple case will also apply to the more realistic setup of the real world. Okay, so the degrees of freedom of a gravitational theory can be roughly approximated by counting the number of independent components that you have on the Riemann tensor. So this is the relation that you get in terms of the space-time dimension, and I'm going to be taking d equals 2 in such a way that this is the minimum number of non-trivial free components that you can have. Okay, so in 2 dimensions it happens to be that just having the metric is not enough. It's not the most convenient thing, let's say, but apart from the metric, one usually considers an additional field called a dilaton, and it is this scalar over here. And the most general covariant action that you can have for such a theory is written in this way. Okay, so we have an integral over a two-dimensional manifold, then we have a linear term that goes phi times r, and then we have an arbitrary potential. Okay, so if you give me a particular potential, this will correspond to a particular theory. Good. And one of the most famous examples, and it's one that Lenny was talking about in some sense, is JT gravity. Okay, and this is the action for JT gravity. The first term is just a topological term. This S0 is a parameter, and the other thing is the Euler character, that is a topological invariant. So for the moment, let's forget about it. And then we have this action over here that notice that it is linear in the dilatons. Okay, we have phi times r, that is the curvature, the Ricci scalar, plus this parameter 2 over L squared. Okay, so this is so this is a theory that for finite L. Okay, notice that L is a parameter of the theory. The screen of Felipe is not shared. Okay, is that true? Is the screen sharing? Sorry.
We just see a road.
Okay.
We just see a road. Maybe it is your background only. Sorry.
Okay, let me try again. That's not good. I see. Okay, let me see how I can fix this.
Matchbooks usually have this problem with Adobe Connect. It is due to security of your system.
Oh, you mean security? Okay, can you hear me now? Great, and now you should be able to see my screen.
Yes. You can hear and you can see everything. Okay, please continue.
Great. So these are the slides that I was referring to. Okay. So here on the bottom you can see the most general two-dimensional dilaton gravity action that you can consider, where V is a potential, and this is the action for JT gravity. Okay, and there are several features that are super convenient about this action that have made it very successful, and to me there are the following. First, the dilaton appears linearly as we see in the action, okay, and it enforces essentially, this means that it enforces the constraint that the Ricci scalar has to be constant and negative, okay, meaning that all solutions of the theory have to be equal to ADS. This is the first fact. The second fact is that this theory is actually equivalent to a topological gauge theory. This is something that is not obvious from the way I've written the action, but it has been known for a long time. And the third point is that it admits arbitrary finite temperature solutions. And this is important, okay, because it allows us to study and use this model in order to understand features of horizons, essentially of black holes, okay? So we are interested in the L to infinity limit, that this corresponds to the flat space limit, okay? And we want to check whether this property continues to be true in this limit. First, the dilaton still appears linear in the action and therefore enforces R equals 0, okay? Meaning that when L goes to infinity, all the solutions have to be locally flat. The second condition, the equivalence to the topological gauge theory, is still true as well. But we lose the third condition, okay? Essentially, the temperature is no longer free to be a finite value, okay? You don't have like a family of solutions with finite temperature, but instead it is completely fixed to one single temperature. And this is not good, okay? If our objective is to learn about quantum gravity, black holes in 2 dimensions, okay? So we need to perform some kind of modification of the theory. And the idea is we want to fix this problem that arises in the equal to infinity in the flat limit of JT gravity, without spoiling properties 1 and 2. Okay, so that's the plan. And the solution to such a problem was obtained a long time ago in the 90s by Cangemi and Jackiw, okay, and it's given by the action that I've written over here. Okay, so let's look at this action. First, let's forget about the first term, okay, because it's the same. Then we still have this linear dilaton, okay, phi times r. But apart from this, we see that then we have another contribution that comes from another set of fields. We have this psi, okay, that is an additional scalar that has no kinetic term and also appears linearly. And then we have this abelian gauge field A, okay, that it is in the way it appears in the action, it is a topological gauge field, okay. So let's the features that this action has, that from now on I will call CJ gravity, are the ones listed over here, 1, 2, and 3, okay. And the main thing that adding this scalar psi and this abelian gauge field A are buying for us is that now the solution, the theory, admits arbitrary temperature, finite temperature solutions, okay? In order to get a little bit of more intuition about the theory, let's look at the field of content and the equation of motion. As I said, we have the metric, and for the metric, the equation of motion is extremely simple. It just tells you that the solutions have to be locally flat, r equal to 0. For the dilaton, we get this differential equation that is linear and quite simple and very analogous to the thing you obtain in JT gravity. Okay. And then we have this additional scalar psi that I will call a frozen scalar, and the reason for that is because the equation of motion for this scalar is simply telling us that the scalar has to be constant. Okay. And finally, we have the abelian topological gauge field that whose equation of motion simply tells you that the field strength F has to be constant. So even though this action, this CJ gravity action, might seem a little bit intimidating at first because we have these 4 fields appearing in this very particular way, we see that the equations of motion are quite simple. Okay. Let me also mention that there is a very simple n=1 supersymmetric generalization of this model where you add a gravitino and a dilatino, okay? And the same kind of logic follows through. The thermal solution is written in this way. I'm using boundary coordinates u and r, that is the radial coordinate. And from here we see that the inverse temperature of this solution is 2 pi over lambda, where lambda is simply the integration constant, is the value of this frozen scalar. And the crucial fact is that since this is an integration constant, the value of beta can take arbitrary values. And this is the kind of Penrose diagram that represent the solution that are written over here. And as we can see, we have this kind of horizons, okay, that are analogous in some sense to the setup one obtains for JT gravity, okay, where the main difference is that instead of having these asymptotically flat regions, you have the ADS regions for JT gravity. Good. So this is the classical theory. And what we want to do next, the main reason we're interested in this toy model, is because we want to analyze quantum fluctuations of this in this theory. In order to do that, we're going to go to the Euclidean theory, and that means taking this boundary coordinate, this boundary time, and performing an analytic continuation to I tau, where tau is compactified, and the compactification coordinate is compactified by a quantity beta. And what we're going to be interested in computing is the thermal partition function, that formally speaking is just given by the integral, the path integral over all the fields, weighted by the action, okay? Where here I have singled out this Euler characteristic term that is weighted by S naught, okay? Now, in two-dimensional theories, we can leverage the fact that two-dimensional orientable manifolds are classified only by the number of boundaries and their topology, and their genus, sorry. In such a way that this partition function, this formal expression that we have over here, we can actually expand it in terms of the genus of the different surfaces, okay? Using that we have this Euler character, S naught, multiplied by S naught. So essentially this is an expansion of the partition function weighted by e to the minus S naught. It is perhaps better to have a graphical representation of this expansion, I think it's clearer. So we see, let's say, for where we have only a single boundary, because here I am allowing little n boundaries. If you have a single boundary, you see that the first contribution, the leading contribution, has the topology of a disk, as we see in this first term over here. Then we have another contribution that doesn't have the topology of a disk because a handle, a hole, let's say, has been inserted into the manifold. And you can see that this term is suppressed with respect to the first one. The first one is multiplied by e to the s naught. So if s naught is large, and we're going to be considering s naught large, then this first term is super big. And the second term is e to the minus s naught. Okay, so when s naught is large, it's going to be very small. Okay, and in that way you can continue. Instead of adding one handle, you can add two handles, three handles, and so on. Okay, so this is the kind of topological expansion that we are going to compute. And to compute it, we are going to use the fact that the dilaton appears in the action linearly. Okay, this means that the path integral over the dilaton can be exactly solved. Okay, because it's just the integral of e to the phi, that is the dilaton times whatever we have multiplying phi. And in this case, what we have multiplying phi is simply the Ricci scalar. Okay. So if we pick the contour for the integral over the dilaton to be imaginary, we get an insertion of a Dirac delta, delta of r. Okay, this means that if r is not equal to 0, then there is no contribution to the path integral. Okay, this is for a particular genus G. Okay, so this means that only locally flat manifolds contribute to the path integral, and this is one of the crucial features that will allow us to compute this full topological expansion. And this is completely analogous to what happens in the JT case. Okay? In the JT case, the only difference was that instead of having r, here we have r plus 2 over L squared. And in that case, it meant that the only surfaces that contribute to the path integral were those that were locally AES. Okay, so this is completely analogous. The only difference is that the surface have to be locally flat. Okay, so what we need to understand in order to compute this path integral is to understand the classification of locally flat manifolds. Okay, and luckily this is extremely simple. Okay, this has been known for a very long time. Mathematicians have thought about it for a long time ago, and if we are only interested in orientable and surfaces that are locally flat with boundaries, and that's what we're interested in, okay, there are only two cases. You can have the disk and the cylinder, and that's it. Okay, that means that for all the other cases, let's say where G is equal to 3, this Dirac delta simply has to be 0, okay, because there are no manifolds that can contribute to this term. Practically speaking, if we make a drawing of the setup, if we consider the single boundary case, first, as I said earlier, we have the disk. Okay, and this is going to be non-zero because there are locally flat manifolds that have the topology of a disk, but all the other contributions that we have over here are 0. Why? Because there are no manifolds that you can put on this kind of topology, okay, that are also locally flat. So at the end of the day, we have this following dramatic collapse of the topological expansion, okay, in such a way that the only contributions that we need to compute are the ones corresponding to the disk and the cylinder, and that's it. If we're able to compute these two things, then we're able to obtain the topological expansion of CJ gravity. Okay, and one needs to do this exactly, and similar to JT gravity, one finds that the integrals, the partition functions of the disk and the cylinder, they are reduced to integrals over a boundary mode, which I'm not going to write because I don't have enough time. But one thing that happens is that those integrals are one loop exact due to this theorem. Okay, and let me show you the final result. This is what you get. Okay, here we see the disk partition function is simply, it is scaling as 1 over beta squared. Then we have the cylinder partition function that goes like 1 over beta 1 plus beta 2, and all the other ones are 0 when you have more boundaries. Okay, these calculations were performed in a couple of papers, okay, that I cited over here. let me also tell you that if you add supersymmetry, okay, if you instead of, so the question is this special? Is this only this, the fact that we're able to compute these partition functions, is it exclusive to the CJ gravity case? And the answer is no. If you add supersymmetry, for instance, you can do n=1 CJ supergravity, and you can define the theory, and as shown in this paper, you can essentially perform a very similar calculation and obtain a similar result, which is similar but not the same. And yeah, there are a couple of consequences that come from these results that are very different. One of the shortcomings of this method, though, is that using this you cannot go beyond the perturbative expansion. Okay, as I said, the topological expansion is an expansion. Okay, as any series expansion, it is an expansion in this parameter e to the minus s naught. Okay, so if we want to obtain non-perturbative effects in this parameter, we're not able to do so using this approach. Okay, so in order to bypass this problem, we can try to find a holographic dual for the system, given by an ensemble of random matrices. Okay, and that's what I'm going to describe next, because there is such a holographic dual, and the idea is that given a Hermitian matrix M, the question that we're going to consider is the following: is whether the topological expansion that we computed on the left-hand side for the partition function can be reproduced to all orders in in a perturbative series by an ensemble average, okay, that's indicated by these brackets, of some operator O that depends on the inverse temperature, and of course it also depends on the matrix. Okay, so the question is whether there is a solution to such a question. Okay, whether we can find an appropriately defined ensemble average and an operator O such that this equality holds to all orders in perturbation theory. And for JT gravity, the answer is an affirmative, and this was done in the very nice paper from 2019 by Sad, Schenker, and Stanford. Okay, and we want to address this question for CJ gravity, and the answer, as we showed in this paper, is yes. Okay, if you want to match the gravitational expansion to all orders in the perturbative series, this is what you have to do, and the answer is unique. You have to pick this potential. Okay, this is the potential that determines the ensemble average of the random matrix model, and you have to pick this operator. Okay, notice that this matrix operator essentially has a contribution from m squared, that is the discreteness of the eigenvalues, and then a continuous contribution from p squared. Okay, and since I'm short of time, let me tell you very briefly, for n=1 CJ supergravity, you can also do the same. You get a completely analogous result, and using this kind of matrix model approach, you can capture fine-grained non-perturbative effects of flat space quantum gravity. And I don't have time to explain, but I wanted at least to show you a couple of plots of the Bondi spectrum that you obtain for this theory when using this method. Okay, these are precise numerical calculations that you can do that are telling you detailed information about the spectrum of the Bondi Hamiltonian in quantum gravity, including non-perturbative effects. Okay, so with this, I have some open questions, but I don't want to go over them now. So thank you very much for the invitation, for listening, and if you have any questions, I will be very happy to answer them.
Thank you. Any question? Seems there is no question. Felipe, thank you very much.